All right, so we're going to be talking about Newton's laws and forces, and I will underline the stuff that I want you to write down, okay? So much of what you'll see up here is not going to need to be written down. So our goal is for you to understand what forces are and how they affect the motion of objects. And then we want to talk about Newton's three laws, and Newton's three laws kind of govern how forces affect the motion of objects, okay? So the first thing we've already talked about, a force is a push or a pull. And interestingly, so I do want you to write this down, a force is a push or pull on an object. And you all talk about forces a lot because we all talk about the weight of things a lot, whether it's the weight of us or the weight of something that you're buying at the store or just like general weight. If you go to the gym and you lift weights and you're talking about like 50 pounds, that's actually a force. The weight of objects, we describe the weight of objects in terms of a force. Object that weighs 50 pounds will push down on you with 50 pounds of force if you're holding it. I weigh like 145 pounds. That means I'm pushing on the ground right now with a force of 145 pounds. We can push on things without there being weight involved. I can push on this wall. And if I put a scale, I could push and I could make the scale say like 20 pounds, 30 pounds, 40 pounds. It's not weight, right? Like nothing is standing on the scale. But if I push on the scale, it's going to tell me the force in pounds. In this class, we're going to use a different unit. We're going to use newtons. And it's not super important that you understand how newtons and pounds are related, but what is important is that you understand that they're basically describing the same thing, how hard something is pushing or pulling on something else. We could talk about my weight in newtons instead of my weight in pounds. We're going to talk about pushing and pulling in terms of newtons on things rather than pounds on things. And we'll talk more about that later. One of the things that we figured out about forces a long time ago is that lots of things can push or pull on an object. So objects can experience multiple forces. Most of us are experiencing multiple forces at all times, okay? The one force that affects everybody on this planet, everything on this planet at all times, is the force of gravity. And if you are in the air and nothing is supporting you, you don't have a parachute, you're not standing on a ladder, you're not standing on anything at all, you're basically falling, then there's only one force acting on you. And in our experience, that's basically the only time that we ever have one force acting on us, when we're in the air. And we can make that happen all the time, we do. Like, you don't have to jump from a high point. If I jump up right now, the entire time I'm in the air, the whole time I was in the air, there was only one force acting on me, gravity. But every other moment of your life, you are experiencing at least two forces. The force of gravity and whatever is keeping you from falling. In my case, it's the floor. In your case, right now, it's the chairs you're sitting in. Sometimes we experience more forces than that. If I lean up against this wall, now gravity is pulling me down, and I'm experiencing a force from the floor, which is keeping me from falling, and I'm experiencing a force from the wall as well. You know, if I was holding on to a leash, and at the other end of the leash was a wild buffalo, and the wild buffalo was running toward Caden because it was hungry, then I would be experiencing three forces in addition to the force of gravity. The floor, the wall, the rope that holds the buffalo. And so one of the things that gets kind of crazy is like, how do we keep track of all these forces? And so this you don't have to write down. Down the road, we're going to be using a drawing called a free body diagram. And that free body diagram is going to show things, and it's going to show all the forces that are acting on things. And then we're going to be able to use that to make predictions about how an object's motion will change. Because when we take all of the forces acting on something, and we put all of those forces together mathematically, it can tell us how an object's motion will change. That's going to be the big thing. That's our big push over the next several weeks, is going to be to think about how forces combine and how that combined force will affect the motion of an object. And it ends up being really kind of cool and really kind of fun, especially when we combine it in the context of the project that we're going to be doing, which is the marble machine. All right, so I want to go through Newton's laws, and before I talk about them, I want to show you some stuff from outer space. And the reason is because, remember I mentioned that, that on Earth, things tend to naturally just kind of come to a stop because gravity pulls them down and then friction slows them down. So even if you throw something, eventually it comes back to the ground and then the ground makes it stop. So what happens if you don't have that? If you don't have gravity pulling things down? What happens if you don't have friction pushing or pulling on something?
Inertia.
Yeah, well, inertia is a description of how forces can, how an object's motion resists change. But you're right that definitely has something to do with it. Let's see if I can get, oops, that's not what I wanted to do. Let's see if I can get some volume here. Volume.
Things at rest stay at rest, and things in motion stay in motion, unless those things have a force imposed on them. I have a bag of candy-coated chocolates, one of our favorite things up here. So let me take one or two of these out. Uh-oh. Don't wait for me. Move it out here. Okay. Alright. Let's pretend like I'm on the ground in your classroom. And if I were to take one of these candy-coated chocolates and let go of it, what would happen? Well, it would go crashing onto the ground, wouldn't it? And then when I ate it, it would have to be a dirty chocolate that fell on the ground. The reason that happens to you in your classroom or on the ground is there's a force exerted on the chocolate, and that force is provided by gravity, okay? And that force is always straight down. So if you were to drop the candy-coated chocolate, it would fall to the ground because it has a force imposed on it. But here in the space station and in low Earth orbit, we are under microgravity, which is essentially no gravity, no apparent gravity. So if I let go of the candy, it doesn't fall. It stays at rest because there's no external force on it, okay? Actually, there's a little force because we have fans going, and so the force is provided by the airflow. But basically, there's no force on it until an external force is imposed on it. Like that. Matter it has no motion unless you impose an external force. And actually, my finger is an external force here. So it stays at rest until an external force is imposed. Okay. Well, you're saying, that's just a tiny little piece of chocolate. That's easy, right? What if that little piece of chocolate had peanuts in it? Would that change it? That's a good question to ask, and that's why we run experiments. Answer good questions. So here we have a candy-coated chocolate with a peanut inside. Now, a peanut's pretty heavy, so that's going to make it fall, isn't it? Okay, let's see. No, things at rest stay at rest. Okay, no matter how big they are, no matter if they have peanuts in them, or almonds, or little crunchy bits. Okay?
There's a couple things that I want to point out about this. One is, so that's not a teacher. And he's not like wrong, but there's some oversimplification in what's going on there. For example, he kept saying things at rest stay at rest, but the candy wasn't at rest. It was moving. And in fact, he had a hard time making it stop moving. The other part of what we're talking about with Newton's first law is not just things at rest stay at rest. The other piece is things that are moving will keep moving unless there's some overall force that acts on it. We'll talk about that in just a second. The next piece has to do with how the mass, which is not exactly weight, but I know that's what most of us tend to think about, but the mass of an object affects how much force it takes to change its motion. So we'll watch this one too, and again, this is the same deal. This is outer space. These are not science teachers. So just bear in mind that what they say is an oversimplification. We're going to narrow it down further. We're going to make sure that we get the science right.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
We're going to start with something small. Something you might have at home. Just take a chopstick. We'll go ahead and use our force in our bungee cord here. We'll put it on our bungee. And we'll pull it back. And you can see how fast it accelerates because there's very little mass. Next we'll try a little spaceship. A little more massive, and you can feel it because as you move it, you can feel it, the kind of force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means acceleration's faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Put back the same amount on the force, and here we go. There you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
Okay, so again, there's some pieces to that aren't really the full picture. But what I like about this is you get to see how things are moving in space, where you don't have the force of gravity pulling them down, and you don't have the force of friction slowing them down. So we're going to watch one more. This has to do with Newton's third law. This one, unfortunately, is the most difficult to understand because most people say it incorrectly. And we're not going to go into detail about it today. We're just going to give you a couple of examples. But as we talk about it over the next few weeks, one of my jobs is going to be to unconvince you of the notion that there is a law that says for every action, there's an equal and opposite reaction. Most of you have heard that. Some of you probably remember it. That's not quite right. But they're gonna say that in here. So just be aware of that. What I want you to see is just what happens in outer space. No gravity, no friction. That's the key of these videos. And we're gonna run through our own demonstrations that are a little bit more interesting and more precise.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pairing. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. Going to be object 1 on the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly mass objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I apply the force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you see Newton's third law in space. Now test it out on Earth. See you next time.
Okay, so we're going to talk about these, and as I mentioned before, we're going to talk about them in more detail down the road. What I want to do is just have you write down a couple of very basic definitions so that you can think about them, and then I'm going to show you some simple demonstrations, okay? So the first one is Newton's first law. And what the astronaut kept saying was, an object at rest will stay at rest unless it's acted upon by an external force, which isn't wrong. A better way of thinking about Newton's first law is that it takes an overall force to accelerate an object. We talked about acceleration a couple months ago, and what I said was objects accelerate when they change speed, which means when they speed up or slow down, or if they change the direction of their motion. In other words, if you have an object and it is not experiencing an overall force, its motion won't change. It won't speed up, it won't slow down, and it won't change direction. So that means a couple of things. One is, if there's no overall force, there's no change in motion. Which means we can kind of make some predictions about how things are going to move by sort of guessing what sorts of forces are going to be acting upon them. So here's a little demonstration. I'm going to take this piece of paper, put it on top of this cup, and then I'm going to put a coin on here. And then I'm going to pull the paper out. And what I want to know is what's going to happen to the coin when I do this. Any ideas? What do you think? It's going to drop. Anything else?
It's gonna be yanked by the paper.
It's going to, yeah. So let's look at this because this is really kind of interesting. If I pull this slowly, then absolutely, it drops, and it does get yanked by the paper. It actually, it just stayed on the paper, right? If I do it a little bit faster, it falls straight down into the cup. Why does that happen? Well, the reason that it happens is because while the paper does pull on the coin a little bit, if I do it really fast, that force only acts for a very short amount of time, which means it only changes the motion of the coin for a short amount of time. And as soon as that paper is gone, there's only one force acting on the coin, and that's gravity. So we see this kind of thing all the time. You all do stuff like this without thinking about it all the time. But it's kind of an interesting thing to think about when you when you kind of see things play out slowly. I think the most common example that we see like this is when we slip. We're so used to the idea that the forces that are acting on us are predictable that if you step on something that's slippery, like ice, we just like, we kind of come apart, right? Like even those of you who are really graceful can fall just by stepping on a slippery spot on the pavement. We're not very good at dealing with unpredictable forces. Yeah?
I just would say, so would I be correct in saying that the reason why, going back to the coin and paper thing, the reason that when you pull the paper fast, the coin drops instead of, you know, being pulled by the paper is because the coin is not, you just heard, so I just wanted to say, basically, it doesn't have enough time for its velocity to accelerate.
That's correct. It has to do with the time. Yeah. It's also, there's a little bit less force, as it turns out. Not dramatically less force, but there's a little bit less force because of the fact that it's sliding on the paper instead of being pulled along with the paper. But in this case, if we were to have a really big container and a really big piece of paper, what we would see is it would move with the piece of paper. It's just with a small piece of paper and a small container, it does move. It moves a little bit in the direction that I was pulling the paper, but just not enough to make it fall outside of the cup. The next one is Newton's second law, and what Newton's second law says is two things. The first is that if we exert larger forces on the same object, we'll see more change in motion. So if I take this chair, for example, and I give it a little push, then it speeds up a little bit. If I give it a medium-sized push, then it speeds up a little bit more. And if I give it a big push, then it can speed up a lot. That's half of Newton's second law. The other half of Newton's second law says that things that have more mass require more force to accelerate at the same rate. So if I take this chair and I give it a little push, and then I have somebody come and sit in this chair. Oscar, mind being my assistant? Okay, so have a seat. If I push with just about the same, well, it's really like a lot harder to get that to accelerate. Thank you. So, and we again have all experienced this, like right in a number of different ways. If you've ever ridden a bike, you know, if you have a heavy backpack on, like you're working harder. If you pushed a shopping cart or pulled a wagon, if you've done yard work, you know, it's easier to move the wheelbarrow around when it's empty than it is when it's full of dirt or plants or rocks or something like that. So what Newton's second law says is that the amount of force, the amount that an object's motion changes, and the amount of mass of the object are all kind of related to each other. And the last law is Newton's third law. And Newton's third law is the one that I think is the most interesting one, because it's the hardest one for us to conceptualize. What people normally say is that for every action, there's an equal and opposite reaction. The problem is, when we talk about action and reaction, we almost always think about conscious decisions that people are making. Yeah?
Can you skip it back?
Yeah. So when I talk about a person's action and reaction, that really has nothing to do with Newton's third law, right? So like if I say something to Liam like, I've never liked anyone as much as I like you in my life. You're the best kid ever. What's your reaction to that? A shrug. So there was an action and a reaction. A heartfelt compliment and a shrug, right? For every action, there's an equal and opposite reaction. Or if I push on this pulley, it spins. The action was me pushing on the pulley. The reaction was the pulley spinning. Neither one of those examples has anything to do with Newton's third law. Newton's third law doesn't say that if I do something, something else will happen. Newton's third law says that forces come in pairs. Forces come in pairs. And they occur in pairs between objects. And the two forces happen at the same time. There's not like one force and then another force. They happen at the same time. they're in opposite directions, and they're the same size. Any force you exert automatically has an equal and opposite force that is exerted back on you at the same time. And there's a super easy way for you to test this. You can use your pencil. And here's how I do it. Take my finger, I put it on the pencil, the tip of my pencil, and I'm gonna push, not very hard, but I'm pushing on the pencil, right? So I'm exerting a force on the pencil. And now, I'm gonna take my finger off the pencil and look at my finger. You see how it's dented? That's because the pencil was pushing on my finger. When I complimented Liam with that incredibly heartfelt compliment, there were no forces being exerted. Newton's third law played no role in that. When I spun the pulley, my finger was pushing on the pulley to my right, your left, and that means that the pulley was pushing on my finger to your right, my left. Those are the equal and opposite forces. Every force that exists has a pair. And it doesn't matter what the force is, it doesn't matter what causes it. Gravity is pulling on us. Gravity is caused by the Earth's mass. We are pulling on the Earth at the same time. We are pulling on the Earth the opposite direction that is pulling on us. We're pulling with an opposite and equal force. The Earth is pulling on me with a force of about 70 newtons, or 145 pounds. I am pulling on the Earth, sorry, not 70, about 700 newtons, which is about 145 pounds. And I'm pulling on the Earth with the same force. My body is pulling on the Earth's mass with a force of about 145 pounds. And every single force that exists happens in pairs. And it's really kind of cool. These are the things that we're going to be investigating with your marble machine. So we have the rest of the period to do some work. So I'm going to post this video to those of you who like to think about it, can think about it again later, and people who aren't here can watch it. But I'll be in the shop shortly. So your job is to continue working on your marble machine. And then next week on Monday, we're gonna help you guys come up with a way of diagramming some stuff on your marble machine. If you've looked at Canvas, it's posted for today, but I wanna skip that. And instead, I'm having you guys keep working on building your simple machines. And then on Monday, you can work on doing some schematic diagrams to kind of figure out how you're gonna lay things out. Okay, so grab your glasses, head to the shop.